Hello everyone, welcome to another class in the course of Quantum Theory of Many-Body Systems in Condensed Matter, here at the Institute of Physics at the University of São Paulo. My name is Luis Gregorio Dias, and in today's class we're going to go over Feynman diagrams. We'll start with a review of the time-ordered Green's functions we saw in the previous class, in particular that perturbative expansion in interaction picture where we expanded the Green's functions in orders of the electron-electron interaction term. And we're going to see how we can use Feynman diagrams to express this expansion in a very elegant way. And we're going to define the Feynman diagrams, and we also see that we can express this expansion in terms of Feynman diagrams if we go to the momentum and frequency space by doing a Fourier transform of the time-ordered Green's functions. So let's go right into it. Alright, so let's start by reviewing the time-ordered Green's functions that we saw in the previous class. And there we define the time-ordered Green's functions at zero temperature as the expected value over the ground state of a Hamiltonian. Right, so this is the ground state for H of the time-ordered sequence of AK at time t and a dagger m at t prime, where here we're labeling then my Green's functions with indices k and m from t prime to t. Notice that k is associated with a t and m is associated with t prime, and this second index represents the dagger operator here within the time-ordered operator. And both of these operators are written in a Heisenberg picture, where the time revolution is governed by the Hamiltonian age, of course. And the time-ordered operator, and as we saw, is defined as such. So if t is larger than t prime, then the order is as this: akt times ak dagger at k prime, at t prime. But if the order is reversed, if t prime is larger than t, then we'll get this operator first acting on this, but then we'll get this plus or minus sign, which will be a plus for bosons and a minus for fermions if t prime is larger than t. So every time you have to reorder terms due to, say, one of the times being larger than the other one, and in order to do that order you need to switch to exchange two of the operators. You get a minus sign if these operators are fermionic. Okay, so this is an important point, and we'll see that these minus signs do appear in the Feynman diagrams as well. We also defined the non-interacting Green's functions. And what do I mean by non-interacting here? When we wrote the Hamiltonian, we wrote it in this way: H equals H naught plus H1, and we treated this H1 as a perturbation. And we specifically did the case where this perturbation is precisely the particle-particle interactions. We're thinking of electron-electron interactions where this is a quartic term. So the non-interacting term is when you have only H naught, and that's a quadratic Hamiltonian in our model, say. So this you can in principle diagonalize and get the spectrum, and you know then the spectrum, you know the ground state, like here, H naught, Phi naught. You might even know a few of the excited states as well. But here we're at t equals 0, so we're looking at the ground state. So in principle you can calculate this time-ordered Green's functions g, k, m naught from t time to t, and here we're calculating the same thing as in here, except now that we're using the ground state for this H naught, and using the H naught and the evolution, the time evolution of these operators in the Heisenberg picture. But here still have the time-ordered operator acting on AK at t and A dagger M at t prime. I put this subindex here 0 so that we remember that we're doing the evolution with H naught. And this is natural in the interaction picture actually, so that's why we're going to switch to the interaction picture to write this perturbation series. But this then is an object that we can in principle calculate, right? So the idea then is to expand this object that we might not know how to calculate exactly. We don't know what the ground state of H is, even though we might have an idea what the ground state of H naught is. So we can be able to write this in terms of these, okay? So let's move on. So in the previous class, we also showed that you can write the time-ordered Green's functions that is essentially an expectation value for the ground state of a product of operators written in the Heisenberg picture in terms of this series, this perturbative series in H1, where now the operators are written in the interaction picture. And we even did an example where this H1 would be an interaction term, a quartic term. And here it appears also in the denominator, this time evolution operator, like in the interaction picture from -infinity to +infinity. And all that is explained in the previous class, where you need to use the Gelman and Lowe theorem to argue that you can do this expansion. But once you did, and you try to apply to a Hamiltonian like this one, where you have H naught to be a quadratic term, where in principle you can diagonalize and obtain the ground state, the many-body ground state of it. And H1 is as I mentioned, an interacting term involves a quartic term. 4 operators here, 2 of them destruction operators and 2 of them creation operators. Notice that this matrix element is the integral of the interaction term. So this is say, a Coulomb interaction and at R1 and R2, okay? Meaning that if you have orbitals in real space associated with these states K and M prime and K prime, this is the integral, right? Integral over coordinates R1 and R2 of phi K, the orbital at state K, position R1, orbital at state AM, position R2. These two are the complex conjugate of the orbitals. The potential VR12, and this is VK prime at R2 at R1, and this is the orbital at state M prime at R2. Notice that this can be written in terms of field operators themselves. So this K and M would be precisely the position. So here, instead of phi K, would have the field operator dagger at position R1, a field operator dagger at position R2, and so on and so forth. But this we already did a change of basis, so this is more general. So K and M can be indices for a given orbital. In any case, let me just remind you that here K and K prime are both in the same position, right? And M prime are also orbitals calculated at the same position. They might be different orbitals and different states, but they are calculated at the same position. And here, when you write them in the second quantized form, you pair then K with K prime. Notice that the change here, and M with M prime. And this is important because you have to keep in mind that here, whenever I write k or k prime, so these first two indices in this kind of column here, I'm talking about the same position, while m and n prime are in a different position, say R2. Okay, so this would be important when we take when you draw Feynman diagrams of interaction lines, k and k prime. So the first column here is in a given position, and m and n prime are in another one. One other thing, I noticed that there's a sum here in k and m. Notice also that if I exchange R1 and R2, the integral is the same. So here I have a double counting, if you wish. So if I switch R1 and R2 for everybody, right? This would be the equivalent of changing k prime and m prime and m and k, right? And reordering the thing. So this would give me the same matrix element. So I'll be double counting them. So that's why I put this factor of 1.5 here. And I think in the previous class I didn't put it. So let's keep track of these factors of 1.5. So every time one of these appears, I'll get a factor of 1.5 as well. Okay, so this sets the stage for me to do the expansion using Wick's theorem to evaluate this expected value of these time ordered operators here. And we saw in the previous class how to do that up to first order, right? So the n equals 1 term in this expansion. And we're going to stop there and analyze what we get. So let's see. Okay, so if we do this expansion, of course the n equals 0 term, so there's no interaction. This is precisely the non-interacting Green's functions, the non-interacting case that we defined before. And let's look at the n equals 1 term. Okay, so here I'll have what? I'll have this minus I. Notice here, let me go back a bit. Oops, sorry, there. There's this minus I to the power n, so I'm taking n equals 1, so there's 1 minus I. This n factorial is 1, so no worries about that. But I'll get this factor of 1/2 down. Why? I only have one h1 here, right? One integral in time, ak a dagger m. So there will be minus I over 2 because of this factor of 2. So let's go back. There is. So there's one sum over k prime, m prime, k double prime, m double prime, that it is the interaction. And we had then that time ordered operator with 6 operators. And in the previous class we showed how to use Wick's theorem to break that into pairings of 3 pairs of operators, one with 1 a dagger, one with 1 a with no dagger. And these would be the possible pairings in different times. And what you get then is 6 terms, 3 of them with a plus sign in front, and 3 of them with a minus sign in front. And these minus signs comes from whenever you have to switch do an exchange relative to the original order in Wick's theorem, you get this minus sign. It's all explained in the previous class. So you get these 6 terms here. And now let's see how these 6 terms tells us in terms of what's going on here, right? First thing I want to note, and I mentioned in the previous class as well, is that these first 2 terms involve a non-interacting propagator or non-interacting Green's functions that goes from t prime to t. So this, remember, this is the creation operator. So you're creating here, destroying here. So it goes from t prime to t. And this kind of factors out of these other two terms here. Notice that there's also a sum over k prime and prime, k double prime, k2 prime that's included here if you wish. But the important thing is that these two Green's functions, they do not propagate. They go from the same time, so t1 to t1 and t1 to t1. So this is something that we're going to see. It is essentially not important and will be cancelled by diagrams coming from the denominator. But these other two terms, these other four terms, they two of them are equivalent in pairs, but they essentially carry the information that we need. But now in this form is rather complicated to make sense of what's going on right here, right? You can, if you want to think of these Green's functions in terms of propagator from, say, state, creating a state, a particle with state m at time t prime and destroying it at time at a state k and at time t, then you can, kind of see something going on here, right? So you start from, say, creating the state m at time t prime, then you destroy it at the state m2 prime at time t1. There is something going on here regarding interactions, another propagator, but now this goes from t1 to t1, and finally one that goes from state k prime at t1 to state k at t. That's where you want to end up, okay? So let's define Feynman diagrams that actually account for a process like this and essentially allows us to calculate or to express this term in a more intuitive way, right? But one important thing is this. In principle, I know everything that is written here. I know how to calculate G naught, the non-interacting Green's functions, and I know these integrals V. So, this integration in time would be just, a matter of, once I have the terms there, I could simply evaluate these terms, okay? But here in this expression, there are more terms that I actually need to evaluate. And the Feynman diagrams help out to sort out why that is. So it saves the trouble of, going to a complicated calculation only to find out that we already had done that calculation before and we didn't need to do it again. All right, so let's see how the Feynman diagrams work. Okay, so let's start with the basic diagrams for, in this language of Feynman diagrams. So let's start with this one. This is sometimes called the free propagator. Oops. And we represent it as a line, right? A line that, represents a propagation. Propagation from where to where? Where the propagation from state m created at time t prime, right? So you're creating here over the ground state, m at time t prime. And you're destroying it at a different state, k, at time t. So this is kind of an amplitude for this process, right? It might even be diagonal, right? So you created m equals to k, that would be the diagonal propagation. You create a state k, a particle of state k at time t prime, and let it propagate to state k at time t, where you destroy it. Okay, so that's the idea here. Now, so this you need then to have these indices m and k at the starting point and end point, and t prime at the starting point and t at the final point. Okay, so this is then the free propagator. Now we have the interaction, and that's the interacting line. directing line. So it's a process like this. It involves destroying an operator at state k prime and creating at k. And remember, these are the same positions, right? So this is, let's put it in blue, or let's put it in orange. So this is position R1, right? K and k prime. And then destroying an operator at position at state M and creating at state M prime and creating at state M. I'm using the same letters here, but you know, they are not related, okay? So, and these two, so these ones happen at position 1, and these two, let's put them in what? Let's put them in, well, here, position R2. Okay, so this is position R1 if you want. This is one vertex. This is the other one. So these involve pairs of vertices, okay? And the vertices, what I mean is that this wavy line, the interaction line, goes from 1, and notice that this is 1 and this is 2. Okay, these two indices refer to position 1 and this is position 2. So I often refer to minus I times this amplitude, this matrix element associated with a diagram like that. Don't think of these lines as propagation lines. There's no propagation here, except there's only this interaction. Here is just like two stubs just to mark the states that are going into the diagram, right? So with the ones that I'm destroying. So I'm destroying k prime and m primes, these states. So it's like just a label. And I'm creating an M and K. And they propagate after that, okay? But here, the diagram represents only this green line, all right? One point that is important is that I can twist this green line if I want. So I can kind of rotate these guys, so it doesn't have to be always like this, both legs entering from below and exiting from above. Actually, I can have a situation like this, where you have in this vertex 1, I have k prime entering and k exiting, and at 2 I have m prime entering from above and m exiting from below. You can, this is also equivalent to that. You know, all that matters is with directions they're entering and exiting the vertices. Okay, same thing here. I can go with k prime from above, exiting with k from below, going from m prime from below to m exiting from above. All right, so then if I have 2 of these or 3 of these and 1 of these, I should be able to link them and construct a diagram with, say, 3 propagation lines and 1 interaction line. So let's see how that works. All right, so here we're going to go over all the 6 terms in that first order expansion. So we're taking the term n equals 1 and see what we get. So let's go with the first 2 terms. And as I mentioned, this one factors out. So in terms of Feynman diagrams, what I have just a free propagator from t prime to t, from state m to state k. Okay, so this is disconnected from what I have here. So let's see what I have here. In each of these 2 terms, I have an interaction line. Notice that I have a minus I in front of the whole sum, so this you might want to think that you have a minus I here in front of this guy and a minus 1I here, so you can then represent this as a wavy line, okay? And this I, j, k prime to k double prime and m prime to k double prime will be propagation lines. So let's first represent this guy. So this would be a term that you have something like that, right? So you have you destroy m2 prime, so these are entering the diagram, right? So these are entering. Yeah, this color is not too good. Let's put another one here. Let's put I don't know, this one. Oh, sorry. Yeah, this is not gonna work very well, so let's see if we can do this. Is m double prime and destroying my, and these are exiting, okay? So I'm entering with m2 prime here and entering with k double prime, exiting with k prime, and exiting with m prime as well. Now I'm going to plug in these propagation lines. So I need a line that propagates from m prime at t1, and t1 is going to be this point here, propagating from m prime to m double prime, but I have to go back to the same t1. So this will naturally involve a loop, right? So if I propagate from one time to the same time, I have to kind of go back to itself, so it's going to be a loop. So this loop is going to look like this. It's going to look like this, right? I'm starting at m prime at t1, going all the way around and ending at m double prime with t1. So this is, it makes sense that, you know, also this m prime and double prime, they're entry and exit lines into the wavy line, so this makes sense written as it is. Now the other thing in this term that I need is another propagation line from k prime to k double prime, ending and beginning at the same time. So it's going to be another loop. So I go at t1 here, this is the same time as here, that's why it's represented vertically, and then I'll go this way, okay, like this, k prime at t1 and end at k double prime at t1 as well. So it's a loop, except that something happens that, you know, there's a process that I start in a state and that I might end in a different state, okay, in general. So this diagram with two lines and a wavy line represents this process here, okay. Now notice the minus sign over it, but here I have something similar, and I just drew the wavy line diagram here, but now I did it in a twisted form. Remember that I mentioned that something like this is equivalent to, if I twist, say, one of these legs, it would be an equivalent diagram. So that's precisely what I did. I'm actually doing this one. A k prime entering, a k double prime entering, k prime exiting on this side, and then m double prime entering and m prime exiting on this side. Now, why did I do that? Well, because of the way of the propagation lines are written. So this term has a propagation line from m prime to k double prime. So I have to begin and end at the same time. So this is like a vertical line here. So you can think as t1 time, a fixed time is like a vertical line here. So when I go from t prime to t vertically, means that time is increasing. So time increases that way, right? So a fixed time is something at a a horizontal line, so these 2 points at the same horizontal position or same vertical position are points at the same time in my space-time diagram. One important point here that this differs from quantum field theory usually is that in condensed matter we are taking the interactions to occur at the same time. So they're instantaneous lines. So in quantum field theory there will be, you know, also a delay time here, a propagation for a photon, say here, but now this is for us is a delta function. It's a delta function in time. So these lines are perfectly horizontal. So they happen at the same time. All right. This is of course an approximation because for us we're not connecting photons here. Essentially the velocities of electrons in materials is much smaller than the velocity of light, so it is as if this interaction occurs instantaneously here. Okay, having said that, let's try to draw this diagram now. So I have a propagation that goes from m prime to k prime, so I have to start and end at the same time, same horizontal line. So to do this one, I would have to go from m prime and end at k double prime would be something like this. And this one, I would start from k prime and end at m double prime also in the same time would be something like that. Okay. So these are the two diagrams that represent these two processes here. So one wavy line, two propagating lines, times this other free propagator that just stays there. It comes factors out. Okay, so these are the first two terms. So to evaluate these other two, let's start with this one. Start at position m, or state m time t prime, right down here. Okay, m times t prime, and I'm propagating it up to m double prime at time m double prime at time t1. Put time t1. All right. So this one, I'm going to draw the wavy line here that comes from this interaction and the horizontal direction, just to try to remember that this is kind of instantaneous. But I don't want to make much meaning about, you know, horizontal lines here, etc., because many of these propagators start and end at the same time. So in principle, they all should be horizontal lines, but they're kind of hard to draw. So this one, even this one here would be something, is a loop, but would be a loop like this, something like that, right? So yeah, don't take the meaning of, you know, time being the in this direction to extreme limits here, right? After all, we all know there's a slightly delay here, so that, you know, these lines might be a little bit diagonal. But let's try to keep that way for didactical purposes. So I have a wavy line here. Okay. So m double prime enters in one leg. So in that same leg, which is going to be what I called before my point 2, I have something like this, right? So that point 2 and m double prime enters. Oops, here. M double prime enters. There needs to be a m prime exiting that same vertex. Okay. And here I have two lines, one coming in, one coming out. Now let's look at the propagators. One thing I know for sure, that one line that's coming out here would be a state k prime, okay? And this state k prime will propagate to k at time t. So this is our t1. The end of this line is precisely at time t, okay? Now, what happens here in this vertex? The other propagator happens especially at t1, right? And propagates from m prime precisely to k double prime, which is the other line entering this vertex here. So in order not to cross any lines here, I'm going to do something like this. But yet another way to characterize my diagrams, which can be something like that. If I have one line coming in and one coming out here, yeah, saying, oh, this is propagating back on time. Well, not if everything is happening at the same time. I'll put something like that, right? Something like this. Like this. So it would be like k entering, k prime going. Oh, sorry. K prime entering, k going. Same here. M away, m prime entering. So this is also equivalent, right? That the only thing that matters here is the green line anyway. All right, so let's go back there and finish off this diagram here. Then it would be something like this. Like this is almost, should be at the same time here, but it's hard to draw, but it would be a propagating line like this. Okay? Sometimes this diagram, if you consider this, so the important thing is that these two positions are different, even though they're at the same time. But if you would consider them to be, you know, in a space-time diagram, these would be different points in space-time. Same position at the same time, then I could even draw this diagram in a little bit differently. That's usually how it's stated in literature, but let's do it this way for now. Now let's go to this other one. There's a minus sign here, right? Because I might have a loop in this one, and we'll go to loops later. But let's start again at m and t prime. M, t prime. Then I'll propagate to k double prime, to a point k double prime here. K double prime time t1. And then I'll have a wavy line here. Okay. Now I want to go to point k, and this other propagator tells me that the line going to k, oops, sorry, let's put this in yellow, to k t would be something like this, right? And I know that in the vertex that k double prime is entering, k prime must be leaving. Okay, so this is vertex 1. So here things are more clear. So k double prime entering, k prime leaving, and then I'm arriving here at k prime. Okay, what happens to vertex 2? Vertex 2, I should have a m double prime entering and an m prime leaving, right? Now there's this propagator going from m double prime at time t1 to m double prime at time t1 as well, so this gives me a loop. So let me write this here, m double prime entering, okay? Yeah, I say, oh, well, I'm not propagating here in times different than t1. No, this would be a loop in this, at the same time. It's hard to draw, but this would be the other diagram. But the only thing that is really important here is that you do have a loop, okay? There is a loop here. Here, in the previous one, we had 2 loops here and 1 loop here, okay? So let's, keeping in mind the number of loops is important. So to finish this, let's go to this other diagram. And I'm actually going to draw it out, and you're going to see it appearing in your screen. Let's see. There. And you maybe wonder, okay, why did I copy the diagrams from above? Actually, they are essentially equivalent. They're topological equivalent. And here's why. Notice that in this one, I'm propagating from m to k double prime. K double prime enters a vertex in the interaction, and there's a k prime leaving, okay, in that same vertex. In the other vertex, I have a m double prime leaving, and this m double prime propagates to k of t. And of course, then in these other vertex, there's this m double prime entering, as it should, and that gives me diagram. So this diagram is essentially equivalent to that one. The only thing that the only thing is different is that I exchange the vertices, the position of the vertices. This is this position 2, okay, this position 1, and then I exchange the indices k and m. So this is precisely that double counting I was talking about, right? So if you change positions R1 and R2 and indices k to an m exchanged, you get the same contribution, and that's why we have the factor of 1/2 in the interaction. So that factor of 1/2 will essentially account for, if you consider the contribution of only one of these diagrams, and then use the factor of 1/2 to notice that you would have, instead of 2 and the factor of 1/2 to correct it, you just don't use the factor of 1/2 and take only one of them. All right. So that's the idea. So these topologically equivalent diagrams, they are the same contribution. Same thing here, right? Even the minus sign that comes in here, it is the same. So this term is equivalent to this one. The only thing that I'm doing is exchange 1 and 2 and m and k prime. You can check for yourself. So far, we have only these 2 contributions going on. And let me just tell you that sometimes it's better to write this diagram in this form, okay? It's more common to do something like mt, something like this, okay? And then a wavy line here. This is also topologically equivalent. It's the only thing that's not so good here is that, you know, these points are not at the same time. But if you think of them as like coordinates in space-time, right? So like this is a coordinate in space-time, r, t. This is, if this would be real space as well, right? So this is position R1, position R2. These would be coordinates in space-time at different points. because even though you're at the same time, you're in different positions. So this is equivalent to that one that I drew, except here I'm explicitly taking into account that times goes this way and interactions are instantaneous. All right. So, but you might see this other one representing particularly this. This has oh, by the way, this has also one loop. And the main message here is that these are topologically equivalent. Oops, the Portuguese going on there. Equivalent, so it's the same contribution. Same contribution. Okay, so that's the message. Okay, let's move on. So let's go back to these diagrams that essentially disconnected from this propagator here. So I mentioned that these would be canceled out, and let's see how does that work. So if I go a little bit to the side here, yeah, there. These disconnected diagrams essentially come from this term, okay? And again, up to fourth order, this time evolution operator would be something like that. Put an h bar here, but doesn't. It's essentially 1. And where this h1 has this factor of 1/2 that I added here, and has this quartic term. So let's try to evaluate this expected value using Wick's theorem. So now I'm writing it explicitly. 1, right, if the state is normalized and all. There's this minus I, there's this factor of 2. And then I have to evaluate this ground state. So we have 2 dagger operators, 2 non-dagger operators at the same time, right? So you could add a time ordering here, but it is essentially innocuous because you're evaluating these at the same time, okay? Now, if I apply Wick's theorem, then I have 2 contributions. One is I pair, say, AK with AK prime, and that gives me a sign of plus. Why? Because to get AK prime close to AK, I need 2 exchanges, so it's 2 fermionic signs. And so this has the same sign as this. And then I also pair AM with AM prime, so everything's looking okay. And then I can pair AK with AM prime, and for that I need 1 exchange here. So I bring AM close to AK dagger, and that will also bring AM dagger close to AK prime, so I get these other contributions. All right, so each of these contributions gives me a free propagator. So this is GK at time t1 going to K prime, and this is M going to M prime, both at time t1 plus the wavy line coming from the interaction. While this one with a minus sign goes from K to M prime, right? And a free propagator going from M to K prime. All right. So let's draw the wavy lines here, okay? And what do I get? Well, here I have a propagator going from K to K prime. Lines entering the interaction, K prime and M prime, lines leaving, it's M and K. So M prime, M, and I have a propagator from M to M prime, so this will give me this curve, this loop here, okay? Propagator from M to M prime. Now I have a propagator from K to K prime. Oops. So that would be this other loop. So this represents this term. while here I have, again, k prime entering, k leaving, m prime entering, m leaving, and I have a propagator from m to k prime, which would be this, and a propagator from k prime to m prime, which would be this. And these are precisely the disconnected diagrams that I had here, okay, in the first place. All right, so these diagrams will cancel out. Why? Because remember, I have this thing in the denominator. So here I only have the first order term, so would be something like this. Will be multiplying by this series of disconnected diagrams here, and we already see that in the first order. If I go to second order, each one of these diagrams will also be multiplied by something like that, by process like this, but then that would be a second order process that were not included here. It would be something like this times this, and so on. So every diagram here in the series that is topologically equivalent would be multiplying by the series of unconnected diagrams. So you can factor them out, so to speak, and then they would cancel here in the denominator. So everything that counts for my expansion, so I don't need to calculate them. That's the beauty of it. The only thing that counts for the actual expansion are connected diagrams that connect mt to kt, right? And that are topologically inequivalent. So out of the 6 original diagrams, I only need to calculate 2. That's the beauty of, expressing these in terms of Feynman diagrams. So let's go back to the slide. All right, so we saw that out of the 6 contributions for the N1 case, we only have 2 of them that we need to worry about. So these 2 are disconnected diagrams that they're canceled by this denominator, and these 2 are equivalent. So when I add them up and consider only topologically distinct diagrams, I can get rid of this factor of 1/2, okay? So let's lay out the rules to calculate, say, this term n equals 1, or the other ones n equals 2, 3, and 4, using the Feynman diagrams. So these are summary of the rules, okay? I'll try to summarize. So the first thing is to calculate the nth order term in the expansion. You draw all connected and topologically distinct diagrams with n interaction lines, beginning at mt prime and ending at kt. Okay, so with n equals 1, we have only one wavy line, the interaction line, and you only get 2 distinct diagrams, the ones that we already saw. Then you associate indices k, k double prime, k3 prime, well, etc., to all the interaction, the 2n vertices in the interactions, right? So if you have n interaction lines, you have 2n vertices. You have, for each one of these, you have to assign a indices that go in and out of the vertex, all right? Obeying, remember that, being consistent with the fact that, you have vk, k prime, vk prime, k double prime, and prime and double prime. This is one vertex, this is the other one, etc. Then to every continuous line going from a state and a time, in a given time, notice that if you have n equals 2, you have 2 wavy lines at 2 distinct times, dt1, all right? And then you associate a free propagator, a non-interacting Green's functions, growing from k2 t2 to k1 at t1. Then to every interaction line, you associate this minus I. This minus I comes from this minus I to the n, times this integral of ek m prime, k double prime, and double prime. Of course, that these indices will depend on which vertices are you considering for that particular line. And then you sum over all indices and integrate of all these intermediate times dt, and you then multiply each diagram by minus 1 or f, where f equals the number of fermionic closed loops. And this will give you the correct minus sign coming from Wick's theorem. So that's a very important step, that whenever you have a closed loop like those that we saw in the diagrams, that means that the pairing is such that will give you a minus sign contribution in the when you're pairing that line. Essentially, the pairing that originates that line will get a minus 1, and that's not so intuitive of where the number of fermionic closed loops you have. But if you look at the way that Wick's theorem essentially disconnects the operators, you see that this makes a lot of sense. So, and at last you multiply by the 1 over n factorial to account for this point. Notice that that factor of 2 is already, a factor of 1/2 in the interaction is already taken into account when you drew only topologically distinct diagrams. So essentially these are the rules for constructing the Feynman diagrams for calculating the n-order term in the expansion. Okay, so to finalize, let's talk about Feynman diagrams in momentum and frequency representation, okay, in momentum and frequency domain. So far we have been talking about time-ordered Green's functions like this one, where you propagate from t prime to t from a given state m, I put here, and a given other state k. But of course you can use the representation in coordinate systems, right? So instead of having a creator operator at some state m, you might have the field operator that creates a particle at position r prime and time t prime. This is in the Heisenberg picture, and another field operator that destroys a particle at time t and position r. So the time ordering here and the expected value over the ground state will give me the propagator from t prime position r prime to time t position r. Okay. Now, if the system is uniform, meaning that of course energy is constant, so if the Hamiltonian is not time dependent, then this would be a function of t minus t prime. And we argue about correlation functions like this. And if the system is uniform in space, this should be a function only of the difference between r and r prime, and not on the coordinates itself. So in the case of uniform systems, and let me write that down here, uniform systems where, say, momentum is a good quantum number, is conserved, momentum is conserved, you can think of a Fourier transform in both space and in time. Of course, if the Fourier transform in time you can always do if this is only a function of t minus t prime, and so you can write this as this, right? So inverse Fourier transform in momentum k of e plus ik. Notice the plus sign here. This is important. If you remember how we did it in previous classes, that's the way you do it. I mean, the direct Fourier transform, there's a minus sign here. The inverse, the one that we are doing here, has this plus sign. Now the inverse Fourier transform in time has this minus sign here. You might also want to look that, so don't get confused, okay? So this is the inverse Fourier transform of this object, which is, oh, sorry, there's an I here. Since I put the I there, I'm going to keep this I here too. All right. Of this object, which is the propagator in K, in momentum and frequency, okay? So it's essentially the Fourier transform of this one. And here I'm writing the inverse Fourier transform. Now remember in the class where we talked about linear response, we also show that when you write it will appear a Fourier transform of the interaction in this form, an integral over dr2 minus r1 of the interaction itself, say the Coulomb interaction here, and we did that precisely for the Coulomb interaction. But here I'm defining this VQ with a plus sign, and that with a plus sign here, okay? So this would be like the Fourier transform with the same plus sign. I try to remember to put the link to that class on the linear response so that you check how this expression appears. But it's like the writing the Coulomb potential in Fourier space, in momentum space as well. And there is this plus sign here in the exponent. So don't get confused with signs, okay? Try to check for yourself and convince yourself. All right, so here what I'm doing, this is the vertex that will enter my Feynman diagrams in this representation in real time. That would be the VR1R2, the actual Coulomb interaction line. So this is position R1. I'm destroying and creating a particle here. So this is our position in real space, R1, and position R2, okay? All right. So how do we actually do that in a diagram and try to transform the contribution for an individual diagram into this K omega representation? So let's see how does that work. So let's take one of those diagrams that we drew, one of the two. I'm taking the one without the loop so that this might be a little bit more clear. But if I go into coordinate space, what I have a propagator that goes from r prime t prime to rt. And there's one line in between. And then I have to assign a coordinates indices for these 2 points. So I'll call this position RA at time t1. And this is position RB at time t1. Okay. So that's what I do here. And there is, then I write the three propagators, right, from R prime to RA, T prime to T1. Yeah, I'm not putting the commas here, but let's put a comma here, and a comma there. Okay. T prime to T1. Then there's the interaction that goes from RA, RB, okay. And then there is this propagator that at the same time, notice this is always propagating at T1, okay? But it goes from RA to RB. There's an I there. And the final propagator goes from T1 to T, from RB to R. Okay, so this is summarize my diagram, but notice that I have to sum over these coordinates or integrate over RA and RB, and also there is an integral over T1 in this contribution as well, and this is going to be important. Okay, so now let's write this, all the Fourier transform of these three propagators and the Coulomb potential, which we defined above right here. Okay, so for each of these, I'm going to write a double Fourier transform like that. So have something like this. Let's start collecting the terms. Let's put it here. All right, so there's this integral in RA, RB, dt1. Here I'll have an integral over what I'm calling K1 and omega 1. okay? An integral over k2 omega 2, an integral over q, right? Due to the Fourier transform of this guy. And finally, an integral over k3 omega 3. Okay, so, I have all these integrals here. Okay, now let's collect the exponentials. For each of these, I have e plus ik r minus r prime, this minus this one, minus I omega t minus t prime, okay? And for this one, I have eiq, or minus iq, right? Because this I want the inverse Fourier transform for this one, r1 minus r2. So what I get then for these three, ik1, r minus rb, ik2, rb minus ra, ik3, ra minus r prime. For this one is e to the minus iq ra minus rb. All right, so that's how we're defining this. The inverse will give you e minus iq. Okay. Now let's look at the frequencies, right? So here I have t1 and t, so minus e omega 1, t minus t1. Here I have something weird, which is equal time propagation. So I'll get like e minus omega 2 times 0, all right? But this 0, if I integrate over omega 2, give me 1, I'm going to get an infinity here. I don't want that. And why do I get an infinity? Because I'm propagating in the same time. So every time I have these same time propagations, I need to add, instead of 0 here, I need to put an eta and take this eta positive down to 0 so that I don't get an infinity here. I regularize my integral, okay? And that's kind of an artifact saying that, okay, this is not actually instant interaction, but it takes a little bit of time, but I'm taking this time to 0. But so that I don't get my integral in frequency doesn't explode, I need to add this one and say do this in a complex plane. So I might get a principal part integral here or something like that. But this is just a technicality. Now here I have different times, so I have t1 minus t prime minus omega 3. All right. Okay. So what do I get? Now I have the Fourier transforms k1 omega 1, k2 omega 2, the propagators, and I have vq, and I have k3 omega 3. All right. So let's see what we can do with these integrals in these intermediate coordinates and the time. All right. So the first thing we notice is that there will be an integral in Ra, and if I collect the exponentials, it will be e to the I Ra. There will be a minus k2 here. This is 2. There will be a plus k3, and there's going to be a minus q. And if I do the integral in Rb, there will be a minus k1, a plus k2, and a plus k. Now these integrals essentially will give me delta functions when I integrate it over Ra, right? It's going to be 0 unless this thing here is 0. And so this actually will be, in a sense, an expression of conservation of a momentum at the vertices. So let's keep that in mind. So when I perform these integrals in Ra and Rb, I get these delta functions that will be, say, k3 equals k plus k2, q plus k2, and k2 is equal, or k2 plus q is equal to k1. That's something that we need to keep in mind. The integral in t1 will also give me a delta function. if I collect here the terms, I'll have plus omega 1 here and minus omega 3 here, so give me a delta omega minus omega 3. All right, so this big thing is just this contribution. And let's see what happens when we deal with these delta functions and put everything into place. Okay, so now I'm writing my diagram in k and omega space. So I have three propagators. One that, this first one is with momentum k3. So let me put a momentum here, and frequency omega 3. This other one is k2, frequency omega 2. The interaction has momentum q, no frequency. And this has momentum k1 and omega 1. Now let's look at those delta functions, right? So the first delta function tells me that k3 minus q plus k2 equals 0. Means that k3 equals q plus k2. Okay? So what does that happen? What does that tell me? That if this is propagating this way, right, with a momentum k3 in this way, at this vertex, it tells me that k2 plus this q is equal to this incoming momentum into the vertex. So this it tells me that there's a conservation of momentum here. This q, I can choose the direction, and I'm going to choose it to be flowing this way, so that, this is positive, this is also positive this way, and this essentially k3 entering and k2 plus kq leaving the vertex, the conservation of momentum at this vertex, the momentum conserve in vertex 1, right? This vertex 1 here. Now, the other one, k2 plus q minus k1 equals 0, means that k1 equals k2 plus q is essentially the conservation of momentum in 2. And now this is in vertex 1, and this is in vertex 2. Why q plus k2 equals k1, right? So the incoming momentum in this vertex is equal to the outcoming one. Now that tells me that this direction that I chose for q is a good one, right? So I have momentum conserved here. The other point is that there's conservation of energy here too. So the frequencies omega 3 and omega 1 will be equal to each other, okay? And omega 2 is kind of undefined because of that the same time propagation, but we put this eta there, so we're not going to worry about that much. All right, so let's redraw this diagram in this way. So if I redraw the diagram, what I have now is if I enter here, propagate here with momentum k, which is, I'm calling now k3 equals k, then the momentum of this line will be k minus q, right? So that would be k2, k minus q. The momentum of the interaction line would be q, pointing that way. And then k minus q plus q equals k. From here I can figure out that k3 and k1 should be the same. So I end up with k. Now this diagram I can represent over an integral in dk, right? So if I put all those delta functions there, all that's left is this integral in this coordinate and one integral in the frequency, which is going to be 1 omega 1 and omega 3. This is the same. There's this integral in omega 2 that I mentioned I have to take care with omega 2 eta here. And finally I have the integral in dq from the vertex. So this diagram is represented by this product of three propagators and the interaction. So this will be the contribution of this diagram to the interacting time-ordered Green's functions at momentum k and omega. So with that, we can essentially generalize our rules for building Feynman diagrams in momentum space. And the most important thing to realize is that you will now, instead of associating coordinates to the points, you're going to associate momentum and frequencies to the lines here. And then you conserve momentum at each vertex and conserve momentum and energy at each vertex. So let's see how does that work. And with that, you can construct, these contributions. And of course, all you have to do is to integrate now in momentum and frequency. But if you know, oh, there's an I missing here. If you know the expressions for this one and this one, say the Coulomb potential, we calculate that in an assignment actually, and we're going to do that in the next class, how to calculate this for, say, the electron gas. You can in principle calculate this contribution, right? And that's precisely what we're going to do for the electron gas the electron gas in a future class. All right, so let's see the rules for building Feynman diagrams in momentum space. So these are the rules for the Feynman diagrams in k and omega space. Let me just summarize what we just learned. So to evaluate the nth order term in the expansion for these Green's functions, what do? We, as before, draw all connected topological density diagrams with n interaction lines. Then we're going to associate a momentum and a frequency to each of the propagating lines and q with frequency 0 to the interaction lines. And to every continuous line, you associate a propagator using this index, this k and omega. To every interaction line, you associate the minus IF-USP. So this propagator is already in frequency and momentum representation domain. And to every equal time propagator, you need to associate that I omega eta and take eta to 0 plus, right? So you don't get an infinity in the integral. Most importantly, you apply the conservation of momentum at each vertex, and that will give you delta functions that you will eliminate many of the coordinates that you associated here, all right? And after that, you integrate all over momentum and frequencies. So the delta functions will make your life much easier here when you conserve momentum. So you might only be left with a couple of momentum or independent momentum, so that you have to integrate over. And then, of course, you have to multiply each diagram by minus 1 over f, where f is the loop of number of fermionic closed loops to get the sign for that particular diagram. And then we multiply by 1 over n factorial. So these are essentially the rules, how you calculate this. And in the next class, or in a future class, we're going to do a real-world example for the electron gas, where we can calculate these propagators and these VQs in exactly, and we can then calculate the contribution of these diagrams in momentum and energy space. All right, so that's it for this class. I'll see you next class then.